So now we'll switch to the next talk to be presented by Hemal Shah from Broadcom. He's a distinguished engineer and system software standard architect in the data center solution group division at Broadcom. He leads and manages a team of architects. He's responsible for the definition of product architecture and software roadmap. And before joining Broadcom, he worked at Intel, where he led the development of the system, silicon, software architecture of communication processors, 10 gig controllers, a lot of projects. He has co-authored several OCP specifications, almost 70 plus DMTF specification for IETF RFCs, and a lot of papers. He also is an inventor on 40 plus patents. So let's welcome Hemal, and he will be talking today about Broadcom NIC Technologies for large-scale HPC and AI ML systems. Hemal, please share your slides.
Yep. Thanks, Dr. Panda and everybody. Can you hear me okay?
Yeah, we can hear you. We see you, but not the slides. You can share the slides.
Yes, I'm sharing. Hopefully you should be able to.
Yeah, it is showing up. You need to presentation mode. Yes. Okay.
Okay. Thanks, everyone. And thanks for this opportunity. Keith, your talk before really helps with a lot of the Ethernet related points I was going to make in this talk. In this talk, mainly what I'll focus on, we have been deploying our server NIC for quite some time. Specifically, what I want to focus on in this is our NIC technology for large-scale HPC and AI machine learning system. And what I'm going to do is first I'll introduce the technologies, and I won't get into the product marketing or any of those. There are publicly available data sheet and features you can, but I'll focus on what are the key areas and technologies that we think are needed for HPC and machine learning markets at scale and at large. And RDMA, the key here is as RoCE adoption is increasing, getting mature, there are other aspects that go beyond just RoCE, either from the congestion point, software infrastructure, so I'll touch on that. That's roughly the agenda. I know we are, I'll try to stay on time. We are running a little bit behind. So Broadcom, we have been in Ethernet business for quite some time. For me, personally, Ethernet and RDMA journey has been 25 plus years. Originally, RDMA started with VI architecture, those who kind of remember that. But RDMA has come a long way, and so has Ethernet. What we see with Ethernet now, the speeds, as they're getting into 100 gig and higher, there are low latency implementation of Ethernet, as we were seeing in the previous talk. People designing the endpoints really are able to do a very high packet per second in hundreds of millions or higher. So that brings that high performance that you get from the underlying network. When you add to that RoCE v2, that gives you the RDMA offload, which is from day one, RDMA has been that kernel bypass technology, which allows applications to get access to the NIC, and not only low latency, but low overhead communication you can have. And also with SRIV, that kind of continues because now you can offer at the VM or container level, not only kernel bypass, but you can also bypass the hypervisor and still offer the benefits of RDMA. So that CPU efficiency comes from all these offloads. If you look at the infrastructure, Ethernet has been around for decades, and it has always had that economy of scale. And then infrastructure, the tools, management, the convergence of all the workload on the same fabric, the infrastructure support for congestion control standards, all those are very attractive to users who want to deploy this at scale. And then over the years, what has happened, RDMA initial stage, the software infrastructure was preliminary, primarily around the VERPs model, but now as we are seeing MPI, other communication layers, people are having infrastructure for application offload. So maturity of that software infrastructure also really makes it very attractive for Ethernet, for HPC and AI machine learning market. So that's where really Ethernet is heading. It's deployed at scale in this environment. It's not just storage or RDMA. Is at this point, the way we see it, there are cloud infrastructure application, HPC, of course, AI machine learning applications, storage applications. RDMA adoption is really increasing, and it's mainly driven by all these demands of application and the performance they get from Ethernet. So this is what we have been doing. You can find, we introduced Thor, which is our 200 gig PCIe Gen 4 NIC, and we continue to build on that family. Thor was already the fourth generation of our NetXtreme E NIC. Started with the 25 gig, 25 to 100, 100 to 200 gig, kind of natural evolution of Ethernet NIC speed. While doing that, you support, there are single, dual port, and quad port. I put in here for HPC and AI machine learning market, mostly we have seen single and dual port kind of configuration. The efficiency of pipeline and the speed basically makes, if you really look at the small messages, though Ethernet and as Keith was talking about some of the protocol overhead, in my opinion, really that level, the wire level overhead doesn't matter as much because now you are really looking into your software layer. That's where the latency is being dominated since your pipeline latency and wire latency has been cut really short. So designing at least the low latency data path becomes very important for the NIC. That's what we have designed for. And then, as I mentioned, the high packet per second, having a pipeline which can process minimum size Ethernet packet, 64 byte at 100 million packet per second or more is important, and that results in higher message rate. So those are the core NIC components and pieces. This NIC is designed for not just RDMA, for general purpose market. So we have tons of other offloads, including all the stateless offloads around the flow processing, flow steering, DSO, GRO, different queuing technology, all those specifically. But for when you look at for the market that we are talking about here, of course, RDMA is one of the key full offload. But along with that, we believe you need other things. And those are, you need scheduling and QoS support from the hardware. This allows you to provide some of the quality of service that customers desire, especially when you are running multiple workloads, or if you're running in bare metal environment, but with new kind of architecture where you have multiple root complexes to which a single NIC is being shared. That's where you want to make sure that those kind of QoS capability matches with the endpoint connectivity. And then other two things I'm going to mention here is, as you see in the cloud infrastructure and other where HPC workloads are moving, typically they have basically network virtualization. So you need some type of port in the NIC, which allows you to process those encapsulation, decapsulation for the RDMA traffic, as well as have the ability to do the lookup and action processing. That's where the flow processing, offload, and pipeline comes into picture. And then the last one here on the offload side, there are several use cases of divvying up a single port into multiple partitions, and also within each physical function, SRIV, where you want to have this VF level assignment to containers or VMs, and also combining that with some of the QoS capability. So making sure your RDMA support works in that environment with the policies and QoS capabilities you need. So all these elements go together from the offload standpoint, and having those supported in the NIC really makes it widely applicable for RDMA related technologies across various markets, including HPC and machine learning. So that's on the NIC and offload side. If you look from the software support side, as I was saying, beyond just the baseline functionality, what we realized you need to have multiple frameworks because the applications that we see today use variety of this software infrastructure, and having support for them, not only having the support, but having very good out-of-box experience where they are getting these packages with the built-in support for the underlying NICs, as well as the tuning aspect that goes with different infrastructure. That's part of providing that software support. And I'll get into it a little bit more in the later slides. That's a really key component for us in terms of not just developing the hardware and having the offloads, but providing all the software infrastructure support. And finally, what I want to mention, as you start getting into scale, congestion control really becomes very important. And when we talk about congestion control, generally people look at it from network infrastructure and looking at the capabilities that you have in the switches. But there are also a lot of things that happen in order to manage congestion at the endpoint, whether it's the rate control, ECN marking, and CNP generation. Those are the capability. Having it in hardware really helps with the congestion control. I'll get into it a little bit more also. But this is really at the core of our technology, where things with around just Ethernet NIC, the baseline functionality, the core offloads I mentioned, and the software infrastructure support combined with the congestion control, that makes it really attractive for this market. As I said, the adoption of this kind of technology is increasing significantly. And then as we are seeing users being more and more comfortable with having Ethernet-based solution, standard Ethernet-based solution be deployed in the HPC and machine learning market. So let me get into some of those specifics. So if you look at RDMA transport that is given when that needs to be fully offloaded in the hardware. The scale here, having 1 billion connection endpoint QPs and going along with that CQs. For the storage kind of market, having large set of SRQs are important. I already mentioned the virtualization support. So what this means is when you have multiple physical functions per port, whether that is because of NPAR kind of technology, or you are connecting to multi-root complex with a shared NIC or multi-host NIC. Having RDMA combined with that, as well as having SRIV where your PF and VF RDMA, and then you have isolation and quality of service between them. So that's all part of the RDMA core offload piece. Traffic management, the way we look at it is from the NIC, you have two sides. You do the host side processing. This is where you're processing the work request and the Wookiees, and then out of that, depending on what operation you are performing, you will generate one or more packets, and they'll go through your pipeline, and then eventually will be transmitted from the port. And receive flow, you can think about it reverse of that. So the idea here is there are different touch points within this where you need to apply QoS policy. And this is where, whether it's the rate limit or the bandwidth sharing, all those come into picture. So in the hardware, what you have is first level, you do the scheduling among multiple functions or multiple processes and the QPs within that. That's how you provide the fairness and QoS. Once that goes through, and then when you are processing those operations, you will be generating packets. Those packets further go through up to 8 class of service per port, where you can have ETS kind of scheduling happening across those class of service. And this provides the further QoS at the network port level. So very flexible kind of scheduling, hardware support, as well as QoS functionality in the hardware. So you can do it at the things like per function level, port level. I mentioned also per class of service. You can also do things like rate limits at the per flow level. This allows, or a group of QPs. And what this allows is the kind of use case where you have specific tenant running this kind of workload. You want to limit all the flows generated by tenant to be not exceeding certain data rate. So this is also very critical component, whether it's a bare metal or virtualized platform. Finally, the flow processing, as I was talking about. What we have built into hardware is once the packets are generated, we do very flexible parsing on per packet basis, and we have identifies whether these are exact match or wildcard flows. And per flow, then we have a set of action that the hardware can perform. The action could be very simple as like you're just counting the statistic for that flow, or could be more complicated. Not only your per flow statistic you are gathering, but also on the transmit side you are encapsulating, and also while doing that you're doing the netting function, and on receive you could be decapping and netting. So very flexible pipeline, which allows us to do flexible packet processing the way it is, both on transmit and receive side. This is the flow it goes through. Once you have the packets on transmit side, after the host processing goes through this. On the receive side, first it goes through this, and then it will be subject to host processing. There are standard flow processing offload infrastructure which we plug into and which are already supported. DPDK, which is user mode, full mode driver infrastructure, which supports RT flow APIs, and Linux has this TC through which the QoS and flow processing offload is supported. And especially if you look from RoCE standpoint, things like RoCE overlay use cases, or whether this is deployed in virtualized environment, you want to, by definition, RoCE is fully executed in the hardware, then you also want to execute all the policies that vSwitch is going to apply also in the hardware. So that's where the vSwitch offload and this becomes, this all comes together. So these are the core PCs for RDMA applications, and those all offloads are in the NIC. Next few slides, I'm going to focus on the software infrastructure. So the baseline infrastructure, as you see, of course, the verbs, user mode library, and kernel module, and our companion control plane firmware, which runs inside the device. That's all very much aligned with Linux kernel. We have been upstreaming this for years. It's part of the User libs are part of OFED as well as next RDMA project. And the advantage here is whether you are using inbox driver for a specific distro or basically using latest version of kernel or specific version of kernel, you do get this built into your RDMA stack. So that's needed for any baseline functionality. And this is one area where continue to also further optimize the software functionality that is coming from the user mode, where the libraries are optimized for things like ability to push small message data, having the data structure optimization in the user mode lib. Those are all part of reducing the latency. Then in the middle, you see I'm showing one communication infrastructure UCX, which is fairly popular, which supports multiple programming model, and the separation of that is there's a high-level API where all this application interface with, and then the underlying you have the hardware transport, and that's where through the verbs driver we plug into, and then the benefit of supporting infrastructure this way, you do not require any modification to the application. Furthermore, our philosophy has always been you should not be, especially around software API infrastructure, the complexity as you start looking into supporting so many, going down the path of creating small here and there proprietary extension, instead of that, we fully rely on having it done through the standard infrastructure. And if there is room for improvement, drive it through the standards, have the community have that infrastructure support built into the framework. So that's how the UCX has been supported. And then all the way to the right, you see MPI, and I took in this example is MBOP-H2, but other MPI implementations is applicable. So MPI has this nice layering of how it interfaces through layers of transport and eventually to the RDMA. And that's where also via the verbs, you enable that framework. There are ways you can think about it can directly face via verbs, or it can go over communication layer like UCX and then use verbs underneath. Either way, it's supported. MPI applications, again, same philosophy. You should not require any modifications to the application or any extension. It should work with the standard framework. We have been primarily testing with 3 key MPI implementation: OpenMPI, MBOP-H2, Intel MPI, and those are all deployed in production also by various customers. One of the things with MPI is it does have its own tunable in terms of the thresholds that you have when you switch from send receive to RDMA read write and others. And those are some of the things, depending on application and MPI libraries, that needs to be tuned. And some of this can be also automated. So that's baseline software infrastructure support, which has been in place for a while and being used by a customer. Recently, in last couple of years, we have seen more and more GPU direct type of compute. And what it means is here you are primarily using GPU compute system where GPUs are doing all processing of all the application level data. And one of the things that you need to, whether it's a GPU or any accelerator, there are several accelerator kind of implementation for machine learning type of application. The memory that they have, typically that is, if you strictly look at all the IB stack, it basically exposes the host memory through the memory management infrastructure. So one of the key aspects here is you need to have peer memory model support in order to provide this, whether you call it GPU direct or direct access to accelerator memory. So today, primarily, we have our peer memory module support, as well as we support the NVIDIA's NVPure MEM. Those are in some of the kernels. It's already available. That being said, there is this DMA buff infrastructure support, which is now available in Linux standard framework. This is basically standard API and infrastructure support, which allows any accelerator memory or any peer to expose its memory to the NIC. And it's based on that export import and fairly simplistic model here and plugged into the IB stack, which allows you to have this kind of peer-to-peer memory data transfer using RDMA. So that is currently our plan, to add that support for our devices, which will enable even much wider variety of GPUs and accelerator. And I also am showing here collectives separately because we have seen beyond just the MPI collectives, there are applications directly using specific collective library, whether it's a nickel or RICL, and we keep seeing different hardware GPU or accelerator having their own optimized collective implementation. So collectives are those libraries use collective operation within a node as well as across node. So for the across node, what we plug into this, you need to have those kind of support, and we enable those via our burst provider and make sure that applications using those collectives directly can leverage the underlying Broadcom Ethernet NIC without any changes to their application. So that goes along with this infrastructure. Excuse me. So that's all about the software infrastructure that we have already in place, and we continue to add more support as there are other infrastructure that comes into market and become popular. So this is all part of developing the solution. The last part I want to touch on is the congestion control. And specifically here, what I'm showing is what are the features or capability that NIC needs to have. The first aspect is the ECN classification. You need to really identify ECN mark traffic or non-ECN mark traffic. In addition, we have the capability to separate them into different class of service queues. Then the other part is traditionally switches have the marking capability, but congestion, there are two different categories of congestion. It can happen in the network infrastructure or in the switches, or an endpoint can also see congestion. And that could be because of various reasons. It could be burst overflowing buffer or PCIe level back pressure that the NICs see. So for that reason, the marking capability we have also extended in the NIC, where NIC can also mark the packets. And then also ability to generate CNPs when you see the ECN mark packet. Those are all having those kind of support in the hardware really makes the ECN-based congestion control scheme enhanced. And that can work in the environment we have where you have either only enabled congestion control only, or you have combined that with PFC. And in the switch infrastructure, we have seen different kind of implementation, whether PFC is enabled only at the first level and then congestion control, ECN marking is enabled in the whole infrastructure, or just using congestion control only. The NIC design that's why it's important to work for all those different modes. And the hardware capability really makes it happen. And the other aspect of that for the deployment is those are all the marking and generation capability, but on the actually endpoint side, you need to also manage the state of congestion on per TP basis. And that's all done in the hardware. And that way you can do real-time update of based on what scheme, whether you're using deterministic scheme like DC-TCP or probabilistic like DC-QCM. Those cancellations are happening in the hardware. And then hardware-based rate control allows you to basically have this kind of deployment in the data center. And that gives you a lot of accuracy and ability to react to congestion faster. And finally, especially with multi-port kind of configuration, what we have seen is you may be plugging into different networks. So you need to have ability to instantiate different congestion control profile on per port basis. So that's where the configurability of parameters that you use for configuring for congestion control comes in the picture. Now, if you just look at it from TCP/IP standpoint, all the nodes I have marked here, they are not part of, but they are implemented in OS stack, and that's why some of the software application, when you see the congestion, it is more conservative and the reaction is much slower. Compared when you have this kind of support in the hardware, Rocky V2 allows you to have very fast reaction to the congestion, maintain low queue depth in the switches as well as NICs, and basically that results in low end-to-end latency. So that was the last piece slide, and let me just quickly summarize. Just to recap, Ethernet at this point is prime for the market that this community is interested in, HPC, AI, and machine learning. I went over our Ethernet NIC technologies, which are mature for this market, and I touched on some of the core offloads, software infrastructure, and congestion control enhancements, which basically are key for success in this market. With that, I'm going to take a pause and
let's thank Hemal.